with some knowledge of the magnetic moment formula and the force on magnetic dipoles and magnetic field, we can get into the Stern-Gerlach experiment. Excuse me, in 1921, Otto Stern, who was actually gotten his PhD in physical chemistry, he actually got it from Otto Sukur, who, if you remember, was the Sukur-Tetrodi equation that we discussed a little earlier, previous lecture. But Stern was thinking about the Bohr theory, actually, Bohr model of the atom, and proposed a method to measure the magnetic moment of an atom, which Bohr theory predicted. Excuse me. And the experiment is something like this. He proposed putting in an oven here, heats the oven up with silver metal in it, heats it up so that the silver melts and finally gasifies. The heat of the temperature that gas at the usual temperature is around 1300 Kelvin, where the silver will become an atomic gas, will vaporize. And of course, they're bouncing around here due to the thermokinetic energy. And so, if you cut a window in this oven, then occasionally one will fly out. It just happens to be going in the right direction. Some fly here, some fly here, and then you direct that through a series of metal baffles that have really horizontal slits coming perpendicular to the page here. Is the usual arrangement. And that is really becomes a collimator that collimates this atomic silver ion beam. And if you compute for these temperatures, I believe the velocity is somewhere around 600 meters per second. So not huge. It's not close to the speed of light or anything. So but huge compared to this width of this non-uniform magnetic field. So in this region, he runs it through, proposes running it through a magnetic field, a non-uniform magnetic field that varies in the z direction, and it does have some components toward the edges that are a little bit different, and especially as we look at how it's produced. But one expects as these atoms come through here that they will experience the force on a magnetic dipole moment and then get deflected one direction or the other, depending on the orientation of the magnetic dipole moment with the direction of this magnetic field, as we'll see. Stern, I have some connection personally to Stern, in that one of my professors, William Levo, who's since passed away, but he was a student of Otto Stern back in the 1940s. So at least one of my professors. So that would make Otto Stern sort of my grandfather in a physics perspective, and I guess to you guys he would be your great grandfather in terms of at least this experiment. Stern, as I said, was a physical chemist, but he soon saw the error of his ways and went to work for Max Born and became pretty much a physicist from that point on, or tended more to the physics side of physical chemistry, might be a fairer way to say it. How did he propose producing this non-uniform field? Well, you can produce a non-uniform field by making an arrangement. If I look at this, now I'm looking at it from the end view, maybe looking in this direction right into the beam from this end. And you make the south pole, the one at the top, sort of an angular with a point to it, and the bottom, they usually put a little circle here. And then the magnetic field for the north pole, and then the magnetic field lines always go from north to south, and so along the circle you get a very strong, there's lots of magnetic field lines here, and so the magnetic field is going to increase as you go in the z direction, which is upward in this picture. And we know that the the force in the z direction is the z component of the magnetic moment times this derivative of the magnetic field. So he creates a non-uniform field, which you have to have so that it doesn't work in a uniform magnetic field. But he doesn't. You don't know what the orientation of these magnetic. Remember, they got a dipole moment. They could have any random orientation as they enter this magnetic field, and so that means that this angle theta could be anywhere from 0 to 180 degrees, basically, or 0 to 360 degrees even. So one expects to have all different size forces, and so the force, if theta happens to be 90 degrees, and the dipole is exactly 90 degrees from the magnetic field direction, then those would go straight through. The very largest force would be when this was 1, and so it would get deflected up to this point, and the very smallest would be negative. The cosine of theta, 180 degrees, would be the smallest, and get deflected downward for a force in the negative direction. Well, how does this relate to Bohr theory if he was trying to compute this in Bohr theory? Let's take a look at the Bohr model and compute the magnetic moment in Bohr's theory. So Bohr's model actually predicts that there's a magnetic moment associated with an atom, a neutral atom. In this case, for us, it would be silver. And you can compute it pretty easily, in that the current is just the charge that moves past a given point in a given period of time. And so here's a charge circulating with velocity v in a circle of radius r, sort of the prototypical Bohr model. And if I get at one point here, the time it takes to go around one orbit is called the period, and so in one period, the total amount of charge that's going to move past a given point is just E. And the ratio of those gives me the current. You can actually compute, we know that the velocity is just distance traveled divided by time. That's just a general formula. But in our case, in the time t equal to the period of one orbit, that it has to go all the way around. So it travels the distance 2 pi r in one period, capital T. And that you can rearrange to get the period in terms of the radius and the velocity. Just solve this for t. And then plug that up to here. And as a result, you get this result, and then simplify, and you get that the current is the charge, in this case the magnitude of the charge, the electron moving with velocity v, divided by 2 pi times the radius of the circle it's moving in. Now from Bohr model, Bohr postulated that the angular momentum is quantized in units of h bar. And momentum is just r times p, or the angular momentum is just r times the regular momentum, and the regular momentum is mass times velocity. And so one could solve this for the velocity. It's just nh bar divided by r, and m becomes the mass of the electron. And then plug that in up here for the v. And that's what I've done here. I just have this expression. But for v, I plugged in nh bar over rme. And after some rearrangement, you get that the current is this. But n could be the Bohr's quantum number, 1, 2, 3, etc. And now then the magnetic moment of that atom is I times the area of the orbit. And that's pretty easy. I just have I, which I've written here. And then the area is just this, area of the orbit is just pi r squared. And so the pi r squareds on top and bottom will cancel. And I get this expression. Basically a constant that is based on fundamental quantities. E, h bar, 2 is just a factor of 2, me. That expression is sometimes given the symbol mu sub b, and it's called the Bohr magneton. And values, if I plug in values for all these fundamental constants, you get this. And so you could write this result in this fashion, that the magnetic moment of this atom in Bohr theory is the Bohr magneton times this quantum number n that Bohr used. Now, as we said, for us then, probably you're just looking at all the atoms being in the lowest possible state, which would be the ground state. So mu in magnitude would be just this mu sub b. And as it goes through the system, one then has this force on it. The force, if you remember, was mu cosine theta times this derivative of the field with respect to z. But you expected all different angles to be accessible. So one expected these orientations to be all possible angles and therefore spread out. And as a result, what one expects then, that the width of this, here in the middle really, should be proportional to the force. The greater the force deflecting it upward, the further it's going to deflect upward. And we know what the force looks like. Theta can be, if we have random orientations, one expects then this total force where you got the maximum deflection, the width of that central piece should be proportional to mu, which for n equal to 1 should just be mu sub b. So Bohr model predicts a situation in which one should be able to measure this maximum width. You would know what these proportionality factors were if you did all of the equations, and that then, from that, you'd be able to get the magnetic moment, and if it matched up with Bohr's prediction, then you would have it. But the experiment itself, one expects to be just sort of spattering of silver all over the place in a pattern that looks something like that. Well, in 1922, Otto Stern and Walter Gerlach. Gerlach was an experimental physicist. They got together and actually built the apparatus and performed the experiment. And what you do is you pull out the glass plate and look for this characteristic pattern on it up here. And the first plate that they did had absolutely nothing on it. They saw nothing. It was just as clear a glass plate as it had been when they started. And while Otto Stern was looking at it, well, apparently Otto Stern was not the richest person in the world. He was just a new professor, I guess. And he had this habit of smoking bad cigars. And why anybody would be smoking a cigar in a physics lab or any lab nowadays would be totally disallowed. But he apparently was smoking his bad cigar while looking at this glass plate that they had just produced that had nothing on it. And as he was puffing on his cigar, well, bad cigars have one thing that makes them bad is they have a high sulfur content. And the sulfur that he was exhaling and the cigar smoke hits the plate, and he suddenly sees these dark lines appear in much the same shape that they were expecting, but nothing filled the in-between. So he was able to take that, compute the maximum width on it. It just happened to be the Bohr magneton, but not not the pattern that they were expecting. They take a photograph of it and immediately send that to Bohr and as some confirmation of his theory, which it really didn't, because it should have had everything in between filled with these with the black. Well, why did it become black? Well, apparently it was the sulfur was combining with the aluminum to get the with the silver to get the silver sulfide, which is a black substance. So that's how a cigar saved a bad cigar saved modern atomic physics.